As I was saying in the previous session, you can normalize these associated Legendre polynomials by multiplying by this term, and so then from well, you can't see it's in the previous session, but I'll just read it out. So integral from -1 to 1 of PML of x, PML dashed of x times PML x dx equals 2 over 2l plus 1 times the factorial of l plus m divided by the factorial of l minus m times the Kronecker delta l dashed. So if you multiply the polynomials, the Legendre, associated Legendre polynomials by this term, and if you then plug in those any two of them for the same m but for different l, this term here, normalization coefficient, if you like, normalization factor, same thing, you'll then get that product being 1, the integral of the product being 1. So these polynomials become normalized, right? Now another bit of information just thrown at you, that there's a recurrence relation between these polynomials of this form. That would be a typical exercise, homework type exercise. You might try proving it yourself if you're interested. So you've got a relation here between different values of L, the associated Legendre polynomials. In this case, L minus 1, L plus 1, and L. Right? Okay. New topic, somewhat. Now, this whole appendix B, is labelled spherical harmonics. Well, what is a spherical harmonic? Well, now we're in the position to explain what a spherical harmonic is. Remember, back in chapter 7, what are we trying to do? We're trying to find the eigenfunctions to L squared, the total angular momentum squared operator, which were simultaneously the same eigenfunctions as LZ hat. And we know those two operators have the same set of eigenfunctions because the commutator of those two operators, L squared and LZ, is 0, right? Those two operators commute. And from earlier theory, we know when that happens, then those two operators have a common set of eigenfunctions. So we're trying to find the eigenfunctions for those two operators. All right? Well, the spherical harmonics are those eigenfunctions. And you may remember when we were trying to solve the eigenequation for both L squared and LZ, we got something of this sort of form. We had a function that depended on the angle theta, and we had another function that depended on the angle phi. And we chose the z component of the angular momentum because its corresponding operator was simple than the other two, the x component or the y component. And we got this as a solution to the LZ, the z component of the angular momentum's eigenequation. It was quite simple. Okay, now we put the two together. So this is a Legendre polynomial. That's the part, the component that depends on theta, and here's the part that depends on phi. Okay, so a spherical harmonic, in a sense, is you take an associated Legendre polynomial like this, and you multiply it by something like this, an exponential to a complex power I m phi. That product here, and you can normalize it, but that product is what's called a spherical harmonic. Okay, and what is a spherical harmonic in this context of angular momentum? It's the eigenfunction. The set of these are the eigenfunctions of L squared and LZ. Right? So that's what a spherical harmonic is. Okay? Now, it's a function of two. What did that happen? Well, okay. My little desk, bedside table light just went on for some weird reason. Okay, so so this state here, it's an eigenstate, an eigen. Oh, I've got a little problem here. Okay. So this eigenstate here, a function of two parameters. So for the eigenvalues m and L, so we can write the state this way, where these are actual eigenvalues, right, for a particular integer L and particular integer m, which correspond to what? L, that's one of the allowed values, eigenvalues for L squared operator. I think I've got that right. There's only two ways, and m would be the allowed eigenvalue, the allowed measured values for the z component of the angular momentum, so LZ's eigenvalue. Okay, so these are actual eigenvalues. Now, so 3 bars. This state, which is a spherical harmonic, you write using the symbol capital Y, right? That's the convention. So you see this capital Y with two parameters, Lm, and this expression here. I mean, this YLm is just this, right? And this factor here, that's just for normalization, right? So when you plug in this, if you integrate two different YLMs, you can make these spherical harmonics orthonormal, right? So that's where you use this. This is just a normalization constant, such that you can make these spherical harmonics orthonormal, normalized, right? So this Y, capital YLM, is defined. Well, it's this. It's just this, right? This YLM is a spherical harmonic, by definition. Now, if you want to do it as homework, to try to evaluate what this normalization factor constant is, it works out to be this, which is a bit involved, right? So -1 to the m square root, blah blah blah. Okay. Now these spherical harmonics, these Y's if you like, they are orthonormal in the following sense. You can multiply two of them and then integrate over a certain way. It depends on the context. And how do you define orthonormal? The definitions depend on what you're doing. Like, for example, these two of these spherical harmonics are orthonormal in the following sense, according to this formula. Right? So you've got like a double integral over angles this time. Phi over 0 to 2 pi and theta over 0 to pi, and a product of two spherical harmonics with L dashed, and here L and M dashed and M. So these two spherical harmonics, they have different L dashes, and different L values and different M values. Okay, and they're both functions of the two angles, theta and phi, obviously. Okay, and they're orthonormal in the sense that the result of this is a product of two delta functions, Kronecker deltas. So delta LL dashed times delta M dashed. So these two M's and these two L's have to be the same for this to equal 1, right? And if one of these is different, if L is different from L dash, or M is different from M dash, or both, this double integral here will be 0. Okay? So in that sense, orthonormal. Okay, so written out here, this is I think still in the appendix. Let me just check. I was switching a bit back and forth between chapter 7 and the appendix. Oh, it just gets referred to in the appendix. Alright, so this now is going back to chapter 7, but it gets referred to, there's a link, a reference in the appendix to this in chapter 7. So here are your spherical harmonics, capital Y, Lm with your two parameters, Lm. So here's the value. What is your spherical harmonic when L is 0 and M is 0? Okay, so 0, 0, that's your simplest one. And you could do this for homework if you want, if you're curious to see where they come from. And you may look at these and say, so what? Well, this is real. If you're interested in chemistry,